So, we start module 1 of lecture 4. In this lecture, we will look at a few more resource constraint scheduling strategies. The first among which is a search based optimal scheduling strategy based on the branch and bound technique. Here we will take the simplistic assumption that a number of resource types is 1, each operation has a unit delay, and we have just 3 operators or resources that are available. So, as we discussed in the last lecture, this takes it to the NP complete domain. So, on 2 resources I can do it in polynomial time, but not on 3 resources. So, how does this solution approach proceed? First, we create a state space considering all possible moves, right? And what do we mean by a state space here? As we said, a state space gives me the different ways of allocating operations to resources at different time steps. So, all the different possible ways, the exhaustive set of possibilities of allocating operations to resources at different possible time steps is the total state space. Now, we do not explicitly create a state space and then search it here. The state space gets implicitly created. A state space tree gets implicitly created as we proceed through the search. Now, however, as we said, we will look as to how we obtain this tree, but given that we obtain a tree, each leaf of this tree, so the state space tree, each leaf of the state space tree holds a feasible solution. How does this hold a feasible solution? The path from this leaf node to the root enumerates a distinct solution, because a distinct path from the root to leaf is a distinct set of allocations of operations to resources at particular time steps. If you have a different path, that different path will give you a different allocation of operations on resources at time steps. Hence, if a leaf node is reached, then we have a feasible solution. That means, we only say that we have not pruned and reached a leaf of the state space search tree, of the state space tree, only if, let us say, my latency bound meets. If my latency bound does not meet given the resource constraint, then I have an infeasible solution. That infeasible solution will not be contained in the state space tree. The leaf node will not hold a valid solution then. So, the path from a feasible leaf node to root node enumerates a solution. The number of solutions is exponential in the number of nodes in the DAG. As we can very intuitively understand that this will be true. And because we can have possibly a huge search space of the state space tree, efficient search techniques are required, as a brute force method can be very time consuming. And hence we arrive at the branch and bound solution technique. The state space tree expansion starts at a state when all operations are unscheduled. So, all operations in the operation constraints graph are firstly unscheduled. We have not scheduled any operation, not ascribed any time step to any operation. Now, we take a set of possible moves, and we can take a set of possible moves depending on the possible choices that we have at a given time. Make a move by choosing one operation among all possible ready to schedule operations. With respect to my operation constraints graph here, what do we have? We choose one of the operations among all the possible operations to schedule. So, let us say if we have 3 resources and let us say 7 operations ready, we can at any given time step we can take any 3 of these 7 ready operations, and this will give me a distinct allocation. So, at any given C step or time step, we have 2 possible moves. What do? We have a set of possible operations, we have a constraint on resources, we take an operation and we can either allocate the operation at this time step if a resource is available, and even if a resource is available, we may choose not to allocate and allocate a different operation. So, for each operation we have 2 possibilities at a given time step. Either you allocate a ready operation on an available resource, or you do not allocate a ready operation on an available resource. Now, whatever decision you take, you suppose I have 4 operations that are available and I choose not to allocate operation number 2. I have 4 operations 1, 2, 3, 4, and we choose not to allocate operation number 2, but allocate operation number 3. Now, on my decision not to choose operation number 2, I need to branch on all possible options that I now have. Now, what do we have? I have 3 more operations, and whatever in whichever ways I can branch, in all possible ways I will branch from that state. What is that state? My move that I will not allocate operation number 2. That brings me to a distinct state, and at that distinct state I have a set of possibilities and I will branch on all those set of possibilities. Now, however, this branching will actually be carried out if the current best solution, as we said, the solution is obtained at certain leaf nodes. Maybe that an initial solution, either we can take the initial solution to be infinite, or we can take the initial solution as the output of a heuristic method and get an initial bound on the solution. And that solution will be what? For example, if we take the same objective as the ILP that we defined in the last lecture, is to minimize the start time of the nth operation. That means is to minimize the length of the entire schedule. If that is the objective, then the current best solution will have a certain time value on what is the schedule length of that solution. Now, if the current best solution in terms of its schedule length is lower than is greater than the lower bound at that state, that means that at a given state I have a set of unscheduled operations. Now, I can obtain a lower bound on the minimum number of time steps that will be required for me to schedule the remaining operations starting from that time step. Why is that so? Firstly, because on the remaining number of nodes I have dependency constraints, and also on the remaining number of nodes I also have resource constraints. So, I can obtain a quick lower bound on the number of time steps that will be required. Now, I already know how much time I have taken to come from the root node to the current node. That means, operations that I have already allocated, I know what is the time that has been taken. Now, the total estimated time for the solution will therefore be the actual time that I have taken to come from the root node to the current state, and plus the estimated time, the lower bound on the estimated time that I have for scheduling the operations from the current step to schedule the remaining unscheduled nodes. Now, that gives me an estimated solution. Now, we say that if the current best solution is better than the lower bound on the estimated solution, it is never possible that I will explore the rest of my search space, the subtree that I have, and get a better solution. In such cases, we can prune the rest of the search tree from this state and look at other places and backtrack to possibly search in other areas of the state space. So, this is the pruning criteria in the branch and bound method. So, this is what we said, that if the current best solution is greater than the lower bound, then what do we do? Then only we search the state space. But if the current based solution is lower, here lower means what? Here lower means that the schedule length is lower, so the solution is better. If the current based solution, if the cost of the current based solution is greater, that means the schedule length is higher, then I will schedule the rest of my search space starting from this state, because there is a possibility that I will get a solution that gives me a schedule length that is lower than the current based solution. However, if the current based solution's value, that means the schedule length, is lower than the lower bound that I have at the current state, I will not expand from the current state anymore, rather I will backtrack and search a different part of the state space. This gives me the pruning criteria. Otherwise, if this is so, we prune or kill the search of the subsequent search tree, and this saves me time with respect to exhaustive brute force searching. In the depth first branch and bound, what do we maintain? We maintain a stack of newly generated states in the state space tree, right. Every operation of the DAG, it is not operator but operation, every operation of the DAG contains the following information: the index number of the node, that means what is the number of the node operation, the ASAP time, the elapsed time, the current time step number, the total number of resources, and the current number of resources available at this time step, which means that I have a total number of certain number of resources, but I have already allocated a few operations to a subset of the resources, say, then I only have a subset of the resources available. This information is also contained in a state. A goal state holds a valid C step value for each operation. That is what we already said, the leaf node holds a valid C step value for all operations. Now, what is the optimal goal state? That goal state, that leaf node, that gives me the minimal C step value. That means that will give me the least schedule length. So, firstly, I have no operations allocated. I have a set of nodes that are ready, independent at the first step. Then what do I do? I choose to allocate one of them. Now, what happens then? If we choose to allocate, the C step value is assigned to the operation's current C step number. So, that operation is now allocated that C step, because I have chosen to allocate it at that C step. The number of available resources is decremented by 1. If the number of allocated resources reduces to 0, we increment time step by 1, and then all resources become available again. Why? Because we have assumed here that all my operations take unit delay, have unit delay. So, therefore, every time step, every operation takes only one time step to execute. Hence, if I have all resources exhausted at a time step and then I increment time, then all my resources become available again. If there are no more ready operations, then increment C step by 1. Now, what is the other way around is this? Because this is the DAG, the maximum possible parallelism given the available resources, it may not be possible to attain at every C step, because I do not have that many ready to schedule operations because of my dependency constraints in the graph. And hence, if that happens, I have to increment time in order to complete scheduling or complete the execution of the currently allocated operations, so that a few more operations become independent and ready to be scheduled. So, as we have been talking about the function in mathematical terms, how do we obtain the cost, the estimated cost at any given state? It is obtained as follows. There is a lower bound function Fn in every state, and Fn is defined as a summation over Gn plus Hn. What is Gn? Gn is the actual cost to reach the current state from the initial state. That means current C step value minus 1. If we have, because we have not already allocated at the current step, we have only actually allocated till the last step. So, the schedule length till now of the operations that have already been scheduled, that schedule length is current C step minus 1. Now, what is Hn? Hn is the lower bound on estimated cost of reaching the goal state from the parent state. For example, how can such an estimate be obtained? A crude estimate. Let us say n be the number of presently unscheduled operations in the DAG. So, I have already allocated and scheduled a set of operations, but there are a set of operations that are left to be scheduled, that I have to schedule, and that is denoted by n. Let k denote the total number of resources that are available. So, then because every operation takes only one time step to execute, so what is a lower bound on the number of time steps that will be required to schedule these remaining n nodes? It is given by the ceiling of n by k. Assuming that there will be no constraints due to the dependency and we will always be able to achieve the maximum parallelism that is available, then this is true, this ceiling n by k. Now, obviously, we see that this can be this Hn, the value of this Hn can be obtained in constant time. However, this estimate is a bit crude. We can still obtain better estimates, but obviously at the cost of higher time complexity. Because why do we talk of time complexity at this point? Because at each step, to calculate each of these heuristic functions, at each step we need to calculate this heuristic function, and the calculation of this heuristic function will therefore consume time at each step. So, this heuristic function, the calculation of this heuristic function cannot take significant amount of time. However, if the estimate is better, then we have higher chances of pruning. Therefore, the heuristic function that we will choose is a trade off between how good the estimate is, because although this is a lower bound, the closer this lower bound is to the actual solution that I will get by actually searching the state space below, and the closer I will get, higher is my chance that I will be able to prune a part of the state space. Because if the lower bound is low, then I have a higher chance that the current based solution will tell me that you have a possibility of searching the remaining state space from this state and get a better solution than the current based solution. However, a better estimate increases the probability of higher pruning. However, again, as I said, there is a cost of generating this solution, this estimate, this heuristic estimate, and hence finding this estimate, how good it will be, is a trade off. So, one good lower bound estimate has been provided in the book. Now, with this we will take a small example. We have this operation constraints graph where there are 10 operations, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have the ASAP and ALAP times that are given in this comma separated, these comma separated numbers beside each node tells me the ASAP and ALAP times. Now, we will take an example to show how a solution strategy that uses branch and bound progresses from the beginning. It is a small partial example. A full example will take lot of space and time. The DAG that we have on the left hand side here, we will use this. All operations take unit time to execute, and we have 3 resources. We said that for a general DAG, this is where is the boundary where the solution goes to the NP complete space. For 2 resources of one type, we can schedule it in polynomial time. We are using this simplistic assumption that we have only one type of resource, but we are now working with the NP complete solution, and hence we are trying to search a large state space systematically using depth first branch and bound. In branch and bound, the basic approach is to enumerate all possible choices at any given state, and for each choice we will branch on all possible options by considering that when we take that choice, what are all the possible ways in which to get the solution, and if we don't take that particular choice, what are the possible ways in which the solution can be obtained. So both the things will be considered, and the solution will proceed with both the considerations. In the previous approach, we said that when we actually allocate a choice is what? For us here, a choice is the allocation of an operation to a particular resource. Now, when we take a particular choice, that is, we actually allocate a certain operation on a resource, we assign a C-step value to the operation, the number of available resources at that time step decreases by 1, and if the number of resources decreases to 0, that means at this time step I have exhausted all my resources, then I must increase time to get back all my resources. And if there are no more ready operations also, I have resources but I don't have any more ready operations, then also I have to increment time to get back my resources, because after the execution of the current operations that are allocated to the resources, the resources will again become free, and currently ready unscheduled operations can be scheduled on those resources. In this example, we can also expand the state space in a slightly different way. This is a resource constraint problem. So at any point in time, I have to exhaust all my resources. So instead of progressing at each time step operation by operation, we can progress time step by time step in this case, because all operations take unit time. Then for example, at the first time step at c equals to 1, which denotes the first time step, and nothing has been scheduled, then our choices are as follows. I can use 3 resources and I can allocate 3 operations to these resources. So the choice 1 is I allocate 1, 2 and 3 to the 3 resources. Choice 2 is I allocate 1, 2, 4 to the 3 resources. Choice 3 is I allocate 1, 3, 4 to the 3 resources, and choice 4 is I allocate 2, 3, 4 to the available 3 resources. So the number of choices here will always be number of available ready operations, C the number of resources. So here the number of choices are 4C3, because the number of independent ready operations at the first step is 4 and the number of resources available is 3. And let us say we first consider choice 1. And then for choice 1, we have 2 options, either to take choice 1 or not take choice 1. So CH1 we can take, or tilde CH1, it refers to the case that we don't take choice 1. So when we take choice 1, that means that operations 1, 2, 3 have been allocated to all the 3 resources, and hence my time will progress by 1 here, and in the second case the available choices will be 4, 5 and 6, and only one choice will be there. Why? Because I have 3 resources, I will always try to maximize my resource usage, because this is a resource constraint problem and we want to minimize time, because this is our objective. We would like to maximize the resource usage at each step, and hence my choice will be 4, 5, 6, and that is the only choice. Now if I don't take choice 1, what happens? I still remain in time step 1. On the left side, because I have actually taken choice 1, so I progress to time step 2. On the right side, I have not taken choice 1, so my time is still at 1. Now the available choices are 2, 3 and 4. Now again I will proceed further. I choose 2 or 3 or 4, any one of them. If I choose 2, then whether I select choice 2 or don't select choice 2, I have 2 options. Now on the other hand, on the left hand side, I am at time step 2 and the only choice is 4, 5, 6. If I take choice 1, I will again schedule, I will make available resource 9, then I will make available resource 7. 7 and 9 will become available at this time step here, at the next time step 3. However, if I don't take choice 1, then I have nothing to do and my solution will just backtrack here, right? Because there is only one choice at this point. So this explains, this small partial graph explains how the state space tree will be slowly expanded to generate all possible cases and exhaustively search the state space. Now, how do we prune? So we said that what is the pruning criteria? The pruning criteria, as we said, was Fn equals to Gn plus Hn, where Gn is the actual amount of time that I have taken to traverse from the root state to my current state, and Hn is a lower bound of the time that I will take to schedule the remaining unscheduled operators from the current state. So we said that Gn is the actual cost to reach the current state from the initial state, and Hn is given by ceiling n by k. What is ceiling n by k? N denotes the number of presently unscheduled operators and k is the number of resources. So n by k tells me the minimum amount of time that I will require to schedule the rest of the nodes. This is how solution will progress.